So we have a matrix and the reduced or echelon form of the matrix, and we want to see what conclusions we can draw about the matrix, and more importantly, how specific we have to be in the things that we write about this matrix. So I chose this matrix for the quiz for a very specific reason, and that is that this last column has a pivot in it. But that's not important because I never said that this is the matrix, the augmented matrix of a linear system or the augmented matrix of an equation. If I want you to look at a matrix and read it as an augmented matrix, I have to tell you, I have to say something like, consider the augmented matrix of a linear system. But if I just say, hey, consider the matrix A and its reduced or echelon form, we're reading this as just a matrix, and we're going to read the pivots of the matrix. All right, so here's what we notice about the matrix A. A has a pivot in every row, and A does not have a pivot in every column. So the things that we notice, A has a pivot in every row. That's one of the things that we notice. A has a pivot in every row. Notice that it's A that has a pivot in every row, not the reduced or echelon form of A that has a pivot in every row. We're trying to make conclusions about the matrix A. We care about the pivots of A. The reduced or echelon form of A has the same pivots, and that's how we found them. But when you're writing your conclusions, you should just say A has a pivot in every row. So what does this mean for the matrix A? Some equivalent statements. I think theorem 4 has a very common type of statement that we're going to encounter. Well, the following are equivalent. So A has a pivot in every row. That means some things. The equation AX equals B is consistent for all B in R, in this case, since A has 3 rows, in R3. That we can conclude because A has a pivot in every row. There's a reason that we can conclude this. The augmented matrix AB will not have a pivot in the rightmost column because we've used them all. But we don't have to state that. We just have to point out that A has a pivot in every row. Therefore, AX equals B is consistent for all B in R3. Now, another important part of this statement is that we're saying AX equals B is consistent. That's not where it ends. We're making a stronger statement. AX equals B is consistent for all B in R3. AX equals B is always consistent would be kind of a more casual way to say that. And this is a conclusion that we drew because A has a pivot in every row. That's where it can end. We could say AX equals B is consistent for all B in R3 since A has a pivot in every row. Now we're done. Anything else we write, we risk messing something up. So if we want to include something else, the reason that we can make this statement is that the augmented matrix, this is because the augmented matrix and I should be specific which augmented matrix, A, B, cannot have a pivot in the rightmost column. So the reason that this is true is that the augmented matrix A, B cannot have a pivot in the rightmost column. That's a good question. So the question is, if there is only a pivot in the first and second row but not the third, can you say that AX equals B is consistent for all B in R2? No, we cannot. B needs to be a linear combination of the columns of A, and the columns of A are in R3. They will always have 3 entries. B will always have 3 entries. So R2 is not a subset of R3. That's a very good question, and it's going to come up in more when we start looking at bases and subspaces. So the reason that AX equals B is consistent for all B in R3 is that A has a pivot in each row. We can only make this conclusion based on the pivots in every row. Some of you were trying to bring in linear independence. Linear independence will not have anything to do with whether this equation is consistent or not. There's a lot of crossover between how things work, not in this case. So the other conclusions that we can draw, we could say, since A has a pivot in each row, AX equals B is consistent for all B in R3. That's a statement about a matrix equation. First of all, we also have to make sure that we specifically call out what equation is consistent. Equations are consistent. Matrices are not consistent. You would not want to say A is consistent for all B in R3. That's an indication that you're mixing consistent with a matrix, and that's not how it works. Consistent only goes with equations. So, next thing, we can also rephrase AX equals B is consistent for all B in R3 by saying the columns of A span R3. The columns of A span R3. Since A has a pivot in every row, the columns of A span R3. This is because AX equals B is consistent for all B in R3. Everything in R3 is a linear combination of the columns of A. So the reason that we say the columns of A span R3, that's the same as saying that everything in R3 is a linear combination of the columns of A. Every vector B in R3 is a linear combination of the columns of A. Every vector in B in R3 is a linear combination of the columns of A. That's what we mean when we say the columns of A span R3. Notice that the subject of the sentence is the columns of A. They're the things that are doing the spanning. The columns of A, a set of vectors, does the spanning. We could also say that R3 is spanned by the columns of A. We still have the columns of A as the subject of the sentence. The reason that every vector B in R3 is a linear combination of the columns of A is that AX equals B is consistent for all B in R3. So saying these two things are equivalent, but we're talking about different things. AX equals B is consistent for all B in R3. That's a statement where the subject is the equation, the matrix equation AX equals B. The columns of A span R3 is a statement about the set of vectors given by the columns of A. So we can say that they span where the equation is consistent. So the other thing that we've added to this, since we started talking about linear transformations, when A has a pivot in every row, we can say the linear transformation given by x to ax is onto. I'm going to say surjective. I'll say onto. Onto is, or surjective, is something that we talk about when we're talking about linear transformations. So the transformation is onto or surjective. Sur being on. So linear transformation is onto. This is because the range of the transformation is equal to the codomain. The range of the transformation is equal to the codomain. This is not something that we would want to include in our explanation. This is just me clarifying what I mean about onto, and also clarifying range and codomain, the distinction between the two. In this case, the range of the transformation is equal to the codomain. What that means is that every b in R3 is the image of some vector in R4. Every b in R3 since A is 3 by 4, the inputs come from R4, the outputs are in R3. So we're saying here that each b in R3 is the image of some vector in R4. And what that means is that AX equals B is consistent for all B in R3. So these are things that we talk about when we see that a matrix A has a pivot in every row. We have a matrix with a pivot in every row, then the equation is consistent for all B in the codomain, or in R3, in this case. The columns of A span R3. The linear transformation is onto, and all those things are equivalents. And which one we invoke depends on what question we're being asked. That was the tricky thing, not really tricky, but that was the thing about the linear combinations 3 quiz. I asked 2 questions in the same way. Question 2 said, do the columns of A span R3? The columns of A span R3 because A has a pivot in every row. Then I asked, is AX equal B consistent for all B in R3? AX equals B, and we would say yes, AX equals B is consistent for all B in R3 since A has a pivot in every row. Any questions? Pivot in every row, something to say about the matrix equation, the set of vectors, or the linear transformation. I do want to point out that we can rephrase this question. The columns of A span R3 is my preferred way of saying it. But we might see this expressed differently. This is equal to saying R3 is spanned by the columns of A. In this case, we're saying the same thing. Grammatically, this is the same thing. The columns of A is what's doing the spanning. R3 is being spanned by the columns of A. So it's the columns of A that's performing the action of spanning. The columns of A is performing the spanning. Surjective is onto. That means the range of the transformation is equal to the codomain. Everything in the codomain is covered. Injective is one-to-one. That's coming up when we point out that A does not have a pivot in every row. Sorry, a pivot in every column. So injective is for a one-to-one transformation. Any questions? Let's see what we can see since by looking at this matrix and noticing that A does not have a pivot in every column. So let's write some things that we can say since A does not have a pivot in every column. So we notice that A does not have a pivot in every column. A does not have a pivot in every column. So that's what we saw here. Some of you said things, started invoking things like free variables, but all you were given was this matrix A. All you're given is this matrix A and the reduced echelon form of A. If you start talking about free variables, my comment was always, what equation are we talking about? Free variables are a thing that belong to the solution set to some equation. If there's no equation in play, we can't talk about free variables without first introducing an equation and talking about its solution set. So let's see what we can say. So we notice that A does not have a pivot in every column. We can say something about the matrix equation AX equals B. We can say something about the columns of A as a set of vectors, and we can say something about the linear transformation given by this matrix multiplication. So the tricky one is the equation one. So A does not have a pivot in every column. The primary things that we want to get out of this is that the columns of A are linearly independent. The columns of A, that was the second thing I did last time, but it's the primary thing I want to notice here. The columns of A are linearly independent. Or sorry, does not have a pivot, are linearly dependent. The columns of A does not have a pivot in every column, so the columns of A are linearly dependent. So let me back up one sec. There's a question about the range equals the codomain. So what I mean when I say that the range of the transformation is equal to the codomain, that means we start off in this transformation takes elements in R4 and assigns them elements in R3. So there's a map from R4 to R3. When the codomain is R3. The range is dependent upon the transformation. So the range of the transformation is the set of all the images under the transformation. So the range of the transformation is the set of images under the transformation. So the range of the transformation is the set of images under the transformation. So if the range is equal to the codomain, that is everything in the codomain is in the range of the transformation, that means the transformation covers everything in the codomain. That's the way we're thinking about it. That's why we use the word onto or surjective. Everything, it takes R4 and puts it onto R3 and completely covers R3. Everything in the codomain is the image of some vector in the domain. And that is the same as AX equals B is consistent for all B in R3. All right. Let's go back and let's talk about linear dependence, and then maybe we'll hit up another example. Another example about range and codomain. So we notice that A does not have a pivot in every column, and so we can conclude that as a set of vectors, the columns of A are linearly dependent. Once again, it's a set of vectors that is linearly dependent. So we wouldn't want to say A is linearly dependent. That doesn't make sense. Linear dependence is a phrase that we should apply to sets of vectors. So we want to talk about the columns of A are linearly dependent. That means one of the columns is a linear combination of the other columns. So the columns, the other way we talk about linear dependence is that one of the columns is a linear combination of the other columns. One of the columns is a linear combination of the others. So one of the combinations is a linear combination of the others. Here's why this is not quite sufficient to conclude that the columns of A are linearly dependent. If I give you this matrix and its reduced echelon form, and you tell me that one of the columns is a linear combination of the others, therefore the columns of A are linearly dependent, that opens me up to ask the question, which vector is a linear combination of the others? What are you talking about? Because that's not readily obvious by what we're looking at here. All we have is the matrix and the reduced row echelon form of the matrix. So we got to remember that we're dealing with a very technical language, even though we can see that this third column is -1 times the first column plus -2 times the second column. What if our reader doesn't see that? We want to remove all doubt. The most efficient thing to do is to say the columns of A are linearly dependent because A does not have a pivot in each column. If you want to talk about linear combinations, then if you're going to say one of the columns is a linear combination of the others, you have to state which one is a linear combination of the others. So in this case, you want to say, namely, first of all, the columns of the matrix don't have any names yet. So we would want to say something like, if A is, say, A1, A2, A3, A4, I have to do this just so I can, if I want to refer to the names of the matrices, the names of the columns. Then we can see that A3 is just -1 times A1 plus A2. Then we can conclude that the columns of A are linearly dependent. Or you might want to say that the third column is -1 times the first column plus the second column. Or the second column minus the first column. But you can't invoke the names of the columns without defining the names of the columns. So what we did here if we want to refer to the names of the columns, then we have to name them. And so that's what I'm doing in this first statement. I'm saying, let's let A equal A1, A2, A3, A4. Then we can see that A3 is just minus A1 plus A2. Any questions? You could also say things like first column, second column, third column, and state your case that way without naming the columns. But if you want to talk about A3, if you started making conclusions saying A3, I'm within my rights to say, what's A3? I don't know what you're talking about with this A3 business. The other thing that we don't want to talk about is free variables, because all I have is a matrix in the reduced echelon form. If you're talking about free variables, you must be talking about some solution set to some equation. And I don't see an equation here to have a solution set to have free variables, because all we're doing is looking at a matrix. Any questions? It only seems like it's a lot to remember because it's a lot to remember. You have to remember all of it all the time, and the language is extraordinarily picky. Maybe that's just me, I don't know. Maybe it's perfectly okay to be all sloppy with your language and say something like A is linearly dependent. After you get out of this class, you can just be like all casual like that and sloppy in your language, and I won't be around to correct you. But until then, since you're in my class, you've got to be careful about what you talk about. I don't want to talk about free variables because all we're looking at is the matrix A in its reduced or echelon form. If you talk about free variables are going to be in the solution set to some equation. And I don't see any equation here. I don't see any equation here. So what equation are you talking about? Cool. And furthermore, the main reason that we're making all these conclusions is that A does not have a pivot in every column. So speaking of equations, we could talk about the equation. There's a lot of things that we can say about the equation. No, linear independent columns will have nothing to do with the transformation being onto. So let me make the comment about transformations. Let's talk about that because there's a lot more to say. There's like multiple things to say about the equation. So we could say the linear transformation, once again, A does not have a pivot in every column. We're focused on the columns. The linear transformation that takes X and sends it to A times X is 1-to-1. 1-to-1 is the column version of columns of, oops, not 1-to-1 because it's not, holy crud. Oh, I can't believe that's on video. You can very cleverly edit this video, post it on YouTube and say, look, my linear algebra professor doesn't know what 1-to-1 is. It's not 1-to-1. So we're deciding whether the transformation is 1-to-1 or not based on the columns. The other word for 1-to-1 is injective. It is not injective. What this means is that two images can come from different vectors. Or sorry, one image will have multiple. One vector will be the image of multiple vectors. So what this means, when we're talking about 1-to-1, that means that each output corresponds to exactly one input. So a 1-to-1 function means each output corresponds to exactly one input. But if the transformation is not 1-to-1, each output will correspond to more than one input. Each output. Let's say each output in the codomain. I wasn't saying output, I was saying image. I forgot the word image for a second there. Each vector in the codomain is the image of more than one vector in the domain. That is to say, t of x can equal t of y even if x does not equal y. The easiest example of a not 1-to-1 function of real numbers is x squared. -2 squared is 4, and 2 squared is 4. So x squared is not 1-to-1. The output 4 has more than one input, 2 and -2. This doesn't tell us anything about the range. This just tells us about how one vector gets to a vector, all the vectors in the domain end up in the codomain. Injective will refer to unique or infinitely many solutions. Surjective will refer to the existence of solutions. It is also correct to say that if a transformation maps onto Rn, you can say that the range of the transformation is all of Rn. That's what it means to map onto. Another thing that this means, if the transformation is not one-to-one, that means that if T of x equals b is consistent, then it has many solutions. So if ax equals b is consistent, then the solution set has infinitely many solutions, because the columns of A are not linearly independent, because the transformation is not one-to-one, because A does not have a pivot in every column. An important thing to notice here is that we need the qualifier. If ax equals b is consistent, then the solution set has infinitely many solutions. And those are the things that we can say about the equation. So if ax equals b is consistent, then the solution set has infinitely many solutions. The columns of A are not, A does not have a pivot in every column. The columns of A are linearly dependent. The transformation is not one-to-one. If ax equals b is consistent, then the solution set will have infinitely many solutions. Another way to say this is to phrase it with the homogeneous equation, which is something that we have to consider with linearly independent or dependent sets. We could say that ax equals 0 has infinitely many solutions. Or the normal way to say it has a non-trivial solution. And if ax equals 0 has a non-trivial solution, then ax equals 0 has more than one solution, which means it must have infinitely many solutions. The thing that we want to note here is that ax equals 0 is always consistent. Ax equals 0 is always consistent. A times 0 always equals 0. Ax equals 0 always has the trivial solution. Ax equals 0 is never inconsistent because there's always at least the trivial solution. The columns of A are linearly independent if ax equals 0 has only the trivial solution. That's why it's very risky to talk about the trivial solution or non-trivial solutions. All right. I want to look at a couple more variations. Are there any questions so far? One of the things that we notice about here, we talk about solution sets. We have to be talking about equations. Talk about solutions, we must be talking about equations, not sets of vectors, not linear transformations. All right, so let's see. Oh, we can also say if ax equals b is consistent, then the solution set has infinitely many solutions. If ax equals b is consistent, then the solution set has free variables. We can also say it that way. But we also always have to qualify it. If ax equals b is consistent, then the solution set, yikes, has free variables. Free variables are a thing that belong to the solution set. Any questions? This is one of the reasons that I keep pointing out. This is one of the reasons that I keep pointing out. You shouldn't use the word it. You shouldn't use the word it. Or they, really, because unless you're perfectly clear as to what you're referring. If you're not sure if you're being perfectly clear to what you're referring, if there is no way to interpret what that it refers to incorrectly, then go ahead. But I got to tell you, it is a big risk to use the word it. If you say something like in this scenario, if I'm looking at this, when I look at this matrix in its reduced to echelon form, you'll say something like it has free variables. But it is the matrix. The only thing that you could be referring to in that sentence is this matrix, because that's the only thing that we have in evidence. So you also might say, if ax equals b is consistent, then it has free variables. At which point the it refers, that you're making a reference to, is the equation ax equals b. The equation doesn't have free variables. The solution set of the equation has free variables. Any questions? A has fewer rows than columns, so A cannot have a pivot in every column. And that's why if ax equals b is consistent, then the solution set will have infinitely many solutions. Any questions? Some of you referred to things like the rank of the matrix because you were exploring the internet, which is always a dangerous thing to do. But you were correct, and some of you were correct in pointing out that the rank of this matrix is 3, because it has 3 pivots. So the rank of A is 3. And then you say, since the rank of A is equal to the rank of the augmented matrix AB, this one here, and they're both 3, then the equation ax equals b is consistent for all b in R3, which is fine and true, but you did not tell me why the rank of the augmented matrix was also equal to 3. Because I could make a rank 3 matrix looking at a matrix and its reduced to echelon form. If there was another row down here, then the rank of A is still 3, but the rank of the augmented matrix might be 4. In which case, your argument falls flat. So you did not prove that the rank of the augmented matrix was also equal to 3. And that's why I marked your answers as incorrect. You can't refer to the rank of the augmented matrix without telling me what the rank of the augmented matrix is. You can't, what you're doing is arguing that ax equals b is consistent for all b in R3 by stating that ax equals b is is consistent for all B and R3. And that's called begging the question. You can't just make your conclusion by making your conclusion, by saying something that's equivalent to that. You have to tell the reader why you are able to make that conclusion. Does that make sense? That's the most important thing. And this is why this whole week I've been pushing read the pivots. Your justifications can all come down to pivots. If your justifications can be covered in a sentence about pivots, then your justifications should be covered in a sentence about pivots. Rows and columns. That's what we're all about. Any questions? I'm going to pause the video and we're going to set up a couple of more examples.